Welcome back. I'm glad you made it to the last of this three-part series. In this last video, we extend the principles we've already used to quantify and understand the crystallization of liquids to understanding transformations where all the phases involved are solids. In particular, we'll see how TTT diagrams for phase transformations in the iron-carbon system can be used to tailor the microstructure and properties of so-called pearlite steels, and how that transformation can be bypassed to form Martensite, the hardest form of carbon steel. In our first two videos, we used examples of the solidification of liquids to understand the key issues involved in phase transformations and their associated TTT diagrams. In this last video, we will look at all solid phase transformations, using what's really a classic example of the so-called Eutectoid reaction in the iron-carbon steel system. In particular, we will learn how to read the TTT diagram for the formation of perlite, where the high-temperature form of carbon-containing iron, called austenite, transforms to a different carbon-free iron phase plus iron carbide, called cementite. We will also use the diagram to show how rapid quenching produces the hardest form of steel, martensite. One of the most studied and most important all-solid phase transformations are those in the FEC steel system, which are classic examples in material science of the correlation between processing, microstructure, and properties. The iron-carbon phase diagram shown here is well studied. At high temperature, there is partial solubility of carbon in gamma iron, where the carbon atoms partially occupy the octahedral interstices of the face-centered cubic structure of iron. However, at low temperatures, when iron transforms to a body-centered cubic structure, the alpha form, there is almost no solubility of carbon, as the interstices in that structure are too small for the carbon atoms. To learn more about why the solubility is so different in these two forms of iron, you can check out this video. What happens when carbon-containing gamma iron is cooled to low temperature? Well, at 727 degrees centigrade, it undergoes a so-called Eutectoid transformation, where the carbon-containing gamma iron transforms into carbon-free body-centered cubic alpha iron plus Fe3C cementite. This is really a very important transformation because as while pure alpha iron is ductile, it is strengthened by the Fe3C precipitates, which are hard and brittle and obstruct the dislocation motion. The transformation requires diffusion of carbon and concentration of the carbon atoms into the regions forming the Fe3C precipitates. This takes time, and as a result, the microstructures and the properties can be controlled by the processing and cooling rate through the transformation. Here is a picture of the structures of the phases involved in the Eutectoid reaction. Below 727 degrees C, the high-temperature gamma form of iron, which is called austenite, transforms into an essentially carbon-free alpha iron, body-centered cubic, given the name ferrite, plus Fe3C cementite. The structures of these phases are quite different to each other, and therefore the transformation must proceed through a nucleation and growth process. As we mentioned, during the transformation, carbon must diffuse and concentrate into the regions that form Fe3C. The easiest way to do this is for the two phases in the product to cooperatively grow side by side and form a lamellar structure, a layered structure. This enables the carbon atoms at the interface with the mother gamma iron phase to diffuse and segregate into the Fe3C forming regions and be depleted in the carbon-free alpha ion regions. This lamellar structure is called perlite, so named because it resembles mother of pearl when viewed under a microscope. Because the carbon atoms must diffuse, the transformation and development of the perlite microstructure is dependent on time and on the degree of undercooling below the equilibrium transition temperature. When the perlite structure nucleates at lower undercooling, lower delta T, and remember the equilibrium temperature is 727, so for lower undercoolings below that, just like we saw previously with the solidification of a liquid, the critical size for growth of the nuclei of the new phases is larger, and therefore less nuclei are formed. In this system, when each of the nuclei grow, they produce the side-by-side lamellae of the two product phases, alpha ion and cementite, and the final structure comprises fewer but wider lamellae. This is called coarse perlite, where the lamellar spacing is typically greater than half a micron, and here's an actual microstructural picture of it. When nucleation occurs at temperatures with a larger undercooling, the critical nuclei size for growth is lower. Therefore, the nucleation rate is faster. There are more nuclei, and the structure has many more lamellae, but with a finer and narrower spacing, about 100 nanometers or so. This is called fine perlite, and is shown on the right. Note the scale marker here, just 200 nanometers, compared to this scale marker for coarse perlite that was 10 microns. Because the interface area between the alpha ion and Fe3C lamellae is much higher in fine perlites, the blocking of dislocations by cementite is much greater in a fine perlite, and the strength of the steel increases, going from coarse to fine perlite. Because of the importance of this system in tailoring the strength and ductility of steels, very detailed TTT diagrams for the Eutectoid transformation are available, and one is shown here. The main features of the diagram are the same as we've seen before for liquid crystallization. Here, our equilibrium transformation temperature is 727 C, and above that temperature, our gamma ion austenite phase is thermodynamically stable. These are the start and finish C curves corresponding to the onset and completion of the growth of the perlite product respectively. Let's identify the phase regions. The area after the finish curve, here, is where the transformation is complete, and it corresponds to the region of stability of the Fe3C plus alpha ion perlite product. The region to the left of the start curve is where the unstable gamma Fe austenite exists, and with time it will transform to perlite. Between the start and finish curves, we have austenite plus perlite. Given perlite is actually two phases, then this is actually a region of three-phase coexistence. These diagrams often contain another C curve between the start and finish curves, corresponding to the time where the transformation is 50% complete. It's basically midway between the two. Now we'll add cooling curves to the diagram to quantify what will happen when a sample is cooled from a temperature above 725 C to room temperature. First, a slow-cooled sample. To this, we can add the points of intersection with the start and finish curve that correspond to the temperature and times for the start and finish of the transformation during this cooling. We'll compare that to a fast-cool sample with its start and finish times indicated here. The slow-cool sample has a higher start temperature, but a longer start time. For the fast-cool sample, growth starts at 642 C, with a nucleation period of, we can read it off, 5.2 seconds. The longer time and smaller undercooling for the slow cool sample result in fewer nuclei, as a larger critical size is required for growth. And after the transformation is complete, this microstructure will be comprised of fewer but wider lamellae. This is the coarse perlite microstructure. For the fast cool, the nucleation is completed at a higher undercooling with a smaller sized and more numerous nuclei, which transform into smaller, narrower lamellae. The final microstructure therefore corresponds to fine perlite. So indeed, by controlling the cooling rate, we can control the actual microstructure, coarse perlite or fine perlite, and therefore control the mechanical properties. We could also use the diagram to quantify the growth times for the two samples. For the slow cool sample, then growth is complete after 76 seconds, with a growth duration then of 39 seconds between start and finish. For the fast cool sample, then the growth is completed after 8.7 seconds, roughly 9 seconds, with a growth time here of just 3.5 seconds, so it happens fast. We had seen previously for liquid solidification, a very fast cool that bypasses the nose of the start curve enables the formation of metastable amorphous glass solids. For the Fe3C system, a very fast quench of carbon-containing gamma ion traps the carbon atoms in the gamma phase, prevents it from diffusing to form the stable alpha ion plus Fe3C phases because it's cooled so fast. This results in a very interesting transformation to a metastable non-equilibrium phase called Martensite. The Martensite structure has a characteristic needle-type structure shown here. We can see a real-time view of the transformation that takes place during the quenching in this video. First we'll watch it at real speed and then in slow motion. Happens fast. Now we'll slow it down and we'll still see the needles appear pretty quickly. Martensite has the highest hardness and strength of any form of iron. However, it's very brittle. The transformation to Martensite takes place without any diffusion of carbon and without any nucleation or growth. And it actually involves a distortion of the austenite structure by the trapped carbon atoms. Such a diffusionless transition is called a martensitic transformation, and there are many other materials that show a similar diffusionless transformation. To learn more about this transformation in these steels, I would refer you to this video, which you can find under my authorship. That concludes this series of videos on phase transformations and reading TTT diagrams. I hope you found them useful and enjoyable. Good luck to you.